Okay, today we are going to talk about exponential growth and decay. And to introduce that, we are going to go ahead and do a few example problems, actually one of exponential growth and one of exponential decay. So if you remember, exponential growth is when you have a function such as the following, with a being greater than 0 and b being greater than 1. So this is for exponential growth. Okay, and then you can have exponential decay, which just has one feature that's different. So a is still greater than 0, and then you have b to the x, but b is actually between 0 and 1. So either a decimal between 0 and 1 or a proper fraction. So that's for exponential decay. So that is just a quick review of the definitions. And so what we're going to do is we're going to actually use these two models to demonstrate some different word problems that have some applications for exponential growth and decay. So let's go ahead and get started. So I'm just going to go ahead and rewrite some of these definitions with a little bit of a different format. So I'm going to say exponential growth Okay, we're going to say that when a quantity increases by a fixed percentage each year, it can be another time period, but usually it's in years, the amount y, okay, or you can use f of x, of the quantity after t years can be modeled by the following equation. So we're going to say y equals a, parentheses 1 plus r raised to the t. So here you have the end amount, we'll call this the end amount, okay, of whatever you're looking at, money, population, what have you. A is the initial amount. R is the fixed percentage rate. Okay, and I'm going to say that it is written as a decimal. Okay, so we got to keep that in mind when you have the percentage, you actually write it as a decimal, and then T is obviously stands for time, so this is time, which is usually in years. Okay, it doesn't have to be in years, but it can be. And one other thing I wanted to say is the set inside the parentheses, the 1 plus r, is known as the growth factor. Okay, and if you actually compare this to the original definition on this page of exponential growth, you have the growth factor being b. That growth factor there is referring to the same thing here. So they're just kind of using different letters. 1 plus r you can think of as your base, your b value. And this actually makes sense because if b is, let me get my laser pointer. If b is greater than 1, okay, we have exponential growth. But if you look here, if r is a decimal, right, and I add 1 to it, then I obviously have something that is bigger than 1 because I'm doing 1 plus something, so it has to be greater than 1, which makes it have b being greater than 1, so that would lead to exponential growth, okay? So let's go ahead and look at an example of something that would involve exponential growth. Okay, so make sure you have your graphing calculator out if you have one. So this example is talking about a population, and there are a couple things that are noted. So first, the initial population is at 191,256,000. okay, in the year 1990. Okay, then you have the fact that the population is growing. So hint, growing would refer to exponential growth at a rate of 1.9% per year. So we are talking in terms of years here. And the question is, predict the population to the nearest 100,000 of Indonesia in 2015. So we want to know, what is population in 2015? Okay, so that's the question that we're going to answer. Okay, so the first thing you want to do is you want to figure out, well, what are the different values that I'm going to plug into the different values for the equation that I was given. And since we are looking at growth here, we know that my equation is going to be the one that I just introduced, where A is going to be the 191,256,000. So it's a pretty big number, which makes sense because it's a population. Then I'm going to have 1 plus R, but R is going to be written as a decimal, 1.9% written as a decimal. If you need to go back and review that, go ahead and look at that. But you move the decimal place 2 points to the left. So it would look like this. All to the T, and if you look here, T, if I'm going from 1990 to 2015, that is 25 years. So T would be 25. Okay, so I'm going to put a 25 up here. And again, I just want to point out that this number here would become something greater than 1, which overall would demonstrate an exponential growth. So just give me 1 second to go ahead and plug this into my calculator, and we'll see what we get. So we have, so on your calculator, you have 191,256,000 times 1 plus 0.019, all raised to the 25. And the answer is, as you expect, it's pretty big. So it is 306,174,959, and it has a decimal 0.2. You don't have to put the 0.2, you can just kind of round it off to a nice number since we're talking about people here. So this is the final answer. Okay, and if you want to, you can write people here since we're talking about people. Okay. Okay, so it's pretty straightforward. You just figure out what the A, R, and T values are, plug them in, and then you get your final answer. In this case, we're talking about a population. So let's go ahead and kind of revisit this definition here and now have a definition for decay. And actually the only difference is going to be this right here. This plus will become a minus, which will make 1 minus something be something less than 1, which based on our initial definition of exponential decay, B would become something between 0 and 1, so it would become decay. So let's go ahead and just make a formal note for exponential decay. So the formula is going to be y equals a 1 minus r to the t. Okay, and I'm not going to write out what a, r, and t are. They stand for the exact same thing, so you can refer to this slide to see what they are. But I will say that we have, instead of a growth factor, we have 1 minus r being the decay factor. Okay, so it's pretty straightforward. The only difference is 1 minus r. So let's just do a quick example involving this. So here's the example. The rate at which caffeine is eliminated from the bloodstream of an adult is about 15% per hour. So we'll say caffeine, oops, Let's make sure I spelled caffeine right. Eliminated about 15% per hour. So in this case, T would be in hours. The next part says an adult drinks a caffeinated soda and the caffeine in his or her bloodstream reaches a peak level of 30 milligrams. So we'll say max caffeine level is 30 milligrams. Okay. And the question is to predict a little bit sloppy here, sorry. Predict the amount of caffeine, okay, which will still be in milligrams, remaining after 1 hour. So we have two parts here. We'll say A after 1 hour from reaching the peak level of 30 milligrams. And part B, very similar question, but after 4 hours from the peak level. Okay, so I'm again just going to go ahead and use this equation here and figure out how much caffeine will be after 1 hour and then after 4 hours, and both of those will be T values. So let's go ahead and do that. So we'll do part A here. So Y is going to be the amount of caffeine in milligrams after so many hours. So A is my initial value of 30 milligrams. It is decaying, hence the minus sign here, at a rate of 15% per hour. 15% is 0.15, and we're interested in after 1 hour. Okay, so if you go ahead and do this in your calculator real quick, 30 parentheses 1 minus 0.15 raised to the 1 will be 25.5 milligrams. Okay, so there's our first answer. And part B is very similar, except T is 4. Go ahead and plug that into your calculator. And you get rounded to the nearest tenths, it's 15.7 milligrams. Okay, and we are talking about word problems here. They have a context, so make sure you include your units. Okay, so there you have two examples. You have an example of exponential growth and exponential decay. The one thing that I will say is sometimes they throw in a question that says, maybe they give you this value here. Let me highlight it. Maybe they tell you what this value is here. So in this case, we'd have, this is 0.75, and they would ask, what is the decay rate? So what you would have to do is you'd have to say, well, I know that R, if they want to know the percentage that it's decreasing every hour in this case, you'd have to set up the equation 1 minus R equals 0.75. And from this, you would find out that R is, I'm sorry, this is 0.85. My fault. So you'd set up this equation here, and then you'd find out that R is 0.15, which is 15%. So sometimes they ask that question too. They'll give you the information, they'll give you the decay rate, and they'll ask what is the percentage that it's decreasing by in this case, or increasing if it was a growth problem. Okay, but there you have it. Those are some examples of exponential growth and decay and their applications.